Well, thank you everybody for coming to hear about non-deterministic parallel programming as a language extension in C. So first of all, just starting off to say, what is non-deterministic programming? What do we mean by this term? And it's kind of a different programming paradigm based around really the idea of ambiguous choice in your control flow of your program. And so the idea behind this is that it allows you to specify some kinds of search problems in a semi-declarative way using nicer syntax to potentially allow for like prototyping more quickly of code or writing cleaner, more elegant extractions of code for expressing search problems, and also being able to automatically gain some amount of parallelism is the goal. And we've implemented this as a language extension to C, utilizing the AbleC framework that our group has developed. And AbleC is an extensible specification of C11 that allows basically independently developed language extensions to be written and composed together automatically by the programmer with different sets of, or to provide different features that could be useful in a program, just sort of like how they might use libraries, but except providing new syntax and new semantics. And it does this by providing a translation down to plain C code. So kind of a motivating example here for non-deterministic programming is Fermat's method of factorization. So this is based around the principle that the identity that any odd integer can be expressed as the difference of two squares. So we have a squared, n is a squared minus b squared, and you can refactor that as a plus b times a minus b. So in the case when n is even, the factors are 2 and the factors of n over 2. If n is odd, we can factor n by non-deterministically choosing some value for a and then requiring that b, which is a minus n squared, ends up being a whole number. So how do we write non-deterministic code? There's a few constructs that the language extension introduces. And throughout this, I'm highlighting in blue all the new keywords that are introduced by the extension. So non-deterministic programs are, the building blocks are non-deterministic search functions, or just search functions for short. Search functions contain non-deterministic statements that are basically, the non-deterministic statements specify a search space as choices in an ambiguous control flow and requirements placed on those choice options that potentially cause some paths of the choice to fail and others to succeed. And yeah, this is basically a domain-specific language. We're extending the grammar of C here. So these non-deterministic statements are only permitted inside a non-deterministic function, search functions. So to actually call a non-deterministic search function from outside of the non-determinism world of things, we have this new invoke expression that basically you provide it with a place to store the result and a function call to a search function, and then also a search driver function. And what that does is a driver function essentially controls the exploration of the search space. And we'll explain that more in a minute. And also currently, this only supports actually recording one successful result of the search, but it would be pretty easy to extend this to store an arbitrary number of results. So two of the other kind of fundamental constructs here are succeed and fail. So search functions don't return a value. You don't use return. Instead, you use succeed with a value or fail, which means that the function did not produce a value in that branch of the search. And a success or failure must be the last statement in the function for reasons that will become clear soon. And also, if you don't explicitly succeed, failure is implicit just by not doing anything. And choice is the other fundamental construct, which basically means that you're non-deterministically choosing between either executing the first statement or the second statement or an arbitrary number of statements here. And so the control, this basically introduces a branch point in the search space. So you can sort of also think about this as when the execution reaches a choice, this is introducing sort of a split of threads, and you can sort of imagine virtual threads that are continuing along executing each of these paths of the logic, or of the control flow of the program, where individual threads can succeed or fail, but they're basically continuing along independently and continuing to branch more. But note though, this idea of virtual threads is something to distinguish from real threads that you might use in a parallel implementation behind the scenes. This is just a way of thinking about it logically. Slight variation on choice is choice 4 when you don't know the number of options, when it varies. So you basically have a choice option for every iteration of the loop. So returning here to our example of Fermat's method of factorization, then, so we have two search functions used to implement this. Range will succeed with all values between lower and upper, and factor succeeds with all the real factors of n. So at the end, when you actually invoke factor, you're going to get a factor of n. You don't necessarily know which one, but the idea is you can potentially call factor from another search function and have some constraints in which factor you're actually wanting to pick, etc. So essentially what's going on here, when n is even, we choose between succeeding with 2 or recursively factoring n over 2, because both are valid factors. Otherwise, when n is odd, we non-deterministically pick a value for a, and its factors are a plus b and a minus b when it was an even value. So now, just to explain what's going on here when I'm saying choose, basically, in order to invoke another or call another search function from a search function, you can't just call it directly within an expression like you'd call a normal C function, because the function can succeed with more than one value. So essentially, we have to immediately bind the results to a variable using the choose statement. And so execution continues from that point from every sort of virtual thread that was created by the call to the function. A slight variation on choose is pick. This is when we really only care about one result of this other search function, or when any result is essentially equivalent. So pick basically works like choose, but cancels all the other threads that are still executing when we have one successful result. And this is quite similar actually to a cut in Prolog. It's a very similar concept. And then finally, there's a couple of shorthands we have. Require just means fail if the condition is not met, otherwise continue. And choose succeed and pick succeed are shorthands for picking or choosing a value and immediately succeeding with it. Now we come to spawn. Spawn is a non-deterministic statement that basically indicates what follows in this thread of execution should be done in a new task. And what this basically means is that instead of just directly continuing on and sort of eagerly continuing to evaluate what follows, we want to instead allow for an external driver function to potentially evaluate the search space in a different order. So spawn sort of pauses the execution at that point, creates a new task, and saves it for the driver function to be able to control the execution. And also note that this doesn't affect the search space, and if you just are writing a purely sequential program where you're fine if it executes in a depth-first search order, you don't need to use spawn. This is just for controlling the order of the search. Also, for those who know what Silk is, it's a parallel programming extension to C. Spawn in this extension is a little bit similar to spawn in Silk, except that there's no corresponding sync operation because you're just spawning off independent tasks that are executing at the same time, but those just go on to succeed or fail by themselves. You're never sort of bringing those independent threads back together. So looking at our factorization example again, so notice that every statement, or all the statements following this choose potentially have to be evaluated more than once for every successful value from range. And so this raises a question then, how do we translate this? So this translation actually works by a transformation to continuation passing style, where instead of directly returning value, functions are parameterized by a continuation closure that should be called with the result of the search function. And this basically allows for the same computation to be continued in more than one way, because we can basically just call the continuation more than once in a non-deterministic choice. Also note, closures here are being provided by another extension to AbleC that is partly inspired by lambdas in C++. So here we see what it looks like when we're actually calling range and choosing a value for it. Essentially, all the following statements here, their translation ends up being what is wrapped up in the continuation closure that is passed into the call to range. Require is pretty straightforward. It just becomes an if statement with all the following statements. Also note this is kind of a basic approach to translation that only allows us to do things in a single-threaded, depth-first way. So in order to actually make this work with tasks, we have to add a little bit. So to allow for potential parallelism or other search orders, we introduce an idea of tasks that are themselves a closure and containing some work to be done, and a task buffer type as a collection of tasks that should be executed. So we parameterize the search functions by the task buffer that's like a schedule sort of tasks, and spawn corresponds to placing all the following statements inside a task that's inside a closure that gets added to the current schedule buffer. So then there's the separate driver function that will be actually reading these and driving the evaluation. So next, we need to think about what search ordering and driver functions do we want to actually write to control this. And it's important to note that there's a trade-off between correctness and being able to reason about termination with some search orderings versus just having better performance by allowing for parallelism or other options for traversing the search tree. So the first option is breadth-first search, which is sort of the most classical idea of non-determinism, where we fully evaluate every level of the tree before moving to the next level. This is great because it always terminates if there's a solution somewhere in the search tree, but unfortunately the performance and memory usage are exponential because you have to store the entire previous layer of tasks before moving to the next level of tasks. You can do multiple tasks in parallel in the same row, and it's fairly straightforward to implement because the task buffer just ends up being a first in, first out queue. An alternative is depth-first search, which has some advantages and some drawbacks. It can, unfortunately, get stuck in an infinite branch of the search tree, even when there is a solution somewhere else. The performance is basically a constant factor better than breadth-first search, but the really great thing is that the memory usage is O of n, because you don't have to store all these tasks that are to be evaluated at some point in the future. Unfortunately, the most basic concept of depth-first search doesn't allow for parallelism, and the task buffer is a little more complex because it has to be basically a stack of queues to make this work. We can modify depth-first search to fix some of these drawbacks, though. So modified depth-first search basically means we perform several iterations of breadth-first search first. So we have some set of tasks that result from those initial layers of breadth-first search. And then we can perform the depth-first search of these tasks essentially simultaneously. This is great because it has some tolerance for infinite branches, and it isn't any worse than depth-first search in terms of termination. But the really great thing is that the performance and memory are asymptotically the same as depth-first search, and you can implement it in parallel by evaluating these individual depth-first searches in parallel. So we implemented a few different search drivers that implement these various search strategies. We have single-thread versions of depth-first search and modified depth-first search, and also a few different parallel versions. There's a version of modified depth-first search, which basically just spawns off tasks from the initial BFS layer in new threads and just lets them run till completion. And then there's a version that does some task sharing, where basically when a thread runs out of work, another thread will notice and provide it with additional tasks to evaluate. Another option is task stealing, where when a thread runs out of work, it goes and actually takes initiative in stealing a task from another thread. However, we just haven't implemented that yet due to lack of time. We evaluated the performance of these search drivers on a few different benchmark applications that kind of represent a diverse set of features. So two of these three are NP-complete, which NP-complete problems actually make for good applications of non-deterministic programming for understandable reasons. And just note, we obviously can't try to get better than exponential performance with these, but we are interested in doing efficient implementations in parallel for potentially small problem sizes. So one benchmark was n-queens completion, which is basically just trying to see for a partially solved n-queens board, does it actually have a solution? And this basically works by non-deterministically choosing and applying valid moves to the board, and then checking if it's solved, and recursively attempting to solve the new board. This has a very high branching factor because you can place a piece in n-queen in any row of the board, and there's only a small amount of work that you have to do at each node. I'm going to skip over this. This is basically the code you use it to make it work. This also uses pick to pick the row that's being placed in. Another benchmark is SAT. Essentially here we're recursively simplifying and evaluating we're recursively simplifying the formula, picking a variable, assigning it to true and false non-deterministically, and doing that recursively. This has a very small branching factor of 2 and a large amount of work at each node. There's also triangle peg solitaire, which we did just somewhere in the middle. So the results of this, the factorization example is actually kind of a terrible application for non-deterministic programming, as it turns out, because this basically means that we have to create a task up front for every single value that we pick or that we choose for the range assigned to A. So we end up with a very wide search tree and waste a lot of memory. So this isn't a very great application for non-recursive search problems. N-queens, basically, you can see the parallel sharing version of modified depth first search did the best. It gave a great performance speed up in parallel. When we tested it on an exhaustive problem with no solution, that's where you saw the real advantage over the spawning application. We also implemented a plain C sequential version to compare it with depth first search, just to measure the amount of overhead. And it turns out there is actually about 40% overhead over like a handwritten C implementation, which is significant, but still this can be quite useful when we're just wanting to write better code and maybe not caring as first priority about speed. SAT and solitaire were similar. There's some future work that we have to implement a task stealing search driver. Maybe we can even try using Silk to do that and use Silk's internal runtime, which is already very well built for doing this sort of optimization. And we also can think about having better abstractions for tasks than just using spawn. There's potentially some more work in that direction. And also potentially even search drivers that do orderings in other orders. So for example, using a heuristic to pick which task to execute first, or even like a randomized search driver might have some useful operations for maybe doing like some sort of statistical non-deterministic problems. But with that, just want to thank you for your attention, and I'm open to any questions. Yes?
I think the value of this kind of DSL is make it easy to do try and error things.
Mm-hmm.
Do you have any experience to do that?
Yeah, so I mean, it was definitely, let me think. So yes, I definitely absolutely agree. That is the main goal of this, is to write code quickly that does this sort of search problems. Anecdotal thing, somebody gave me a puzzle that they wanted solved in order to give back to them, like this cube thing where you have to fit blocks into it. And I say, hey, I'll just try using this extension to do it, because I had messed with doing like writing it in C by hand, and that wasn't going so well. But yeah, this was great for prototyping that. Yeah.
It reminds me a little bit of a subset of TDL. I was wondering if you could compare it to TDL.
I'm not familiar with TDL.
It's at this point sort of old robotics language, but you have tasks and subtasks, and you can do them in parallel. And it's an extension to C++.
Okay. I'll look into that. Sounds interesting.
One last question from the back of the room, please.
Mm-hmm.
If I understood correctly, you are kind of mixing your definition of the search problem with these kind of directives for where you want to spawn, etc.
Mm-hmm.
Can you imagine this kind of more of a language design question, maybe? Can you imagine that you can separate these two so that you
Yes.
instead of mixing the two.
Yes, I think that is a very interesting direction to go in. Yeah, something maybe along the lines like what Halide does, where you have like a definition of the problem and then a separate like schedule for executing it. Originally, spawn was actually implicit with every non-deterministic choice, so it was kind of a last-minute thing, and we realized, okay, actually we can split these concepts apart. So there's definitely a lot of work that can be done in terms of improving that.
The rest of the questions, do not, please. Thank you
Yes.
again.